Alright, a response video of sorts. No real point, but not really, because I'll never get a counter response. But anyway, Professor Lewin, so there's been a few circumstances where, at least he's making videos, which is interesting. And in kind of a way that is critiquable. And so there has been some subjects that have come up in his questions videos. One was on the subject of the speed, not the speed of, redshift, and whether the Doppler effect is equal, emitters versus transmitters. And he claims that in sound it's uneven, where in light it's even. And this is something to do with relativity, where I don't believe that has anything to do with it, of course. But I don't think it's correct. I don't think there's any evidence that in sound there is any different in terms of the amount of redshift created by an amount of movement. Whether the emitter's moving towards or the receiver's moving towards doesn't make any difference. He claims otherwise. Then there's the inductance as a power source in a circuit. So if you use an inductor to energize a circuit, what is the consequences and how can they be measured? He claims that there can be two voltages at the same location in a wire, and I would claim that no, you can go to different locations in the wire and get different voltage, but you can't get different voltages at the same location in a circuit. That's not possible. And now this subject sort of came up about when circumstances that create a change in the r squared rule into the r cubed rule because of some interaction between either charges or gravitational bodies. And I don't think this is right either. And so it's kind of a very complex subject. It gets into tides and the moon and all that kind of crap too. But so anyway, we'll play some of this, and then I'll go to the drawing board, so to speak. So let's just start somewhere in his early explanation. Let me speed it up a little bit. So the idea is just two charges sort of close together, +3, -3. And then at a distance pretty far away, where this distance starts to become irrelevant because this distance is so far. So, it's like 3 feet plus 1 millimeter versus 3 feet. Can't make much difference. It can make a lot of difference when you're 1 millimeter apart. Doesn't make much difference when you're 3 feet apart. And then you have another measurement twice that distance away. And what is the difference between these two? Okay, so it's not the distance between this and this, it's the difference between this and this location, which essentially is the difference between this whole, however you want to define it. Now the trick of this is again, it's not something I think has ever been experimentally demonstrated to be the truth. So it's something that they mathematically say is true, but I don't know if they've ever demonstrated it to be a physical fact. A little complicated to do the experiment, but I think it's quite doable. So anyway, I'll let him say some of that. And so his contention is that this is as long as they're all in the same alignment, that is the two charges plus this straight line, okay, get it? So they all have to be in the same line. And that's what makes the whole thing, in my opinion, doubtful, is because I don't think we know whether the charge from one body actually goes through the charge of another body. The charge actually doesn't travel through charges like it's free space. So in a sense, the one charge will annihilate the other charge from anything that is the same profile. That is, if the charge is this big and the thing is this big, it's never going to be able to see the charge behind the other charge. It has to be much bigger to be able to see it, so to speak, to get anything from it. to be affected by the dipole. It'll only see the monopole. So, and I think this is true with regular magnets. They're stronger at the poles and weaker on the sides, and for a reason. And part of the reason is because of this. The black end is essentially blocking the red end, you know, in a sense, and the red end is essentially blocking the black end. All right, so we'll play some of this.
Here too, I define x equals 0. On the x-axis, very, very far away, is a point capital R, and capital R is way larger than t. And even further away, there is a point on the x-axis, x equals 2r, twice as far away as this point. And my question...
So it's how far they are away from this 0, which is the distance in between the two charges. So from the point in between the two charges, let's see how much of this is showing. Well, enough of it, you can get the idea. So the point in between the two charges to this, and then the other distance is twice that distance. And he says it's an r cubed rule, and that the thing further apart, so these two are this far apart, and the charged things are over here, whatever. And that this one is essentially getting 8 times less force than this one by that scenario, when by the r squared rule it would be 4 times. All right. So I don't know if we need all the explanation parts. Let's play maybe some of it.
To add that vectorially to a plus E field. And now, since capital R is much, 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 much smaller than G, the dependence of the E field will now fall off as 1 over R to the power 3.
Right, so he said smaller than D, he meant bigger than D, so there's a couple of semantical, we'll call them, errors.
It's not so intuitive why it is 3, but you have to agree that it must fall off faster than 1 over R squared. And if you don't see that, remember what I just said, that each charge individually, the E field falls off as 1 over R squared, but they're in opposite directions. And the difference is very small. And
all right, so what I would argue, so we'll go to the drawing table, and I'll sort of point out my grievance with this analysis that, again, I don't think has ever been, I don't think there's any physical evidence demonstrating this to be true. So it's just a mathematical model that says so. And I don't think the mathematical model takes into account the stuff that's part of reality that their mathematical model doesn't include. All right, so the idea would be is that you have a charge positive, let's say, and that you have a negative. And what you're trying to ascertain is what is the effect on this thing out here, something out here. And so, again, it's really sort of dependent on how you think the force, number one, travels. Now, I'm going to argue that obviously the force on all these things travels in straight lines. And, you know, so whatever effect they're having is a straight line force. So my argument would be is that this force coming off of this object is not going to get through this object as if it wasn't there. So it's not like you're actually combining two forces. So if they were in free space at some different angle, you would just combine them because of superposition rules. You could just add them, subtract them. But because they're actually physically obstructing each other, okay, so it's not like you're saying here's another charge over here, what's the effect of this dipole? Well, you can see that the dipole's forces are going to interact, and you know, you're measuring over here somewhere. You can see that the energy going this way that might be blocked by this is going to be irrelevant. The energy going this way is going to be blocked by this is irrelevant. So you're just going to have energy plus energy, which obeys the superposition rules. But when you line them up, now you're creating this idea that you actually have an obstacle in the way of this force. And can this force go through the obstacle would be my argument. I would say it can't. That force will be dissipated from the positive charge in some manner like this, and it won't just travel this way. And the only thing you're going to feel from this charge, this negative charge, is the fact that what might happen, okay, is that as you bring a positive and a negative charge within proximity to each other, what's going to happen is the charge is going to tend, okay, to move to this side. So you're going to have more charge on this surface than on this surface. So that's going to change, and vice versa. There'll be more charge on this surface. But this surface can't get through this surface, so it doesn't do it any good. So all you end up with is this surface, this charge, but reduced. So this negative charge is going to win anyway. So they both have the same charge, 3. You know, so it's a charge of minus 3. Alright, and plus 3. Right, red pen, blah 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 blah. And so what are you going to sense, say, at this distance, is this plus 3 charge minus the fact that the charge has moved to the other side more than this side. So it's going to have less charge density, let's say. It's going to be a little weaker coming out of here than out of the other side. And so then you would end up with something weaker than the r squared rule, in the sense that this charge is diminished by the fact that it's uneven. And so you'll measure it as something less than r squared, but something more than r cubed. So it's not going to be one or the other. It's going to be something else. And it really doesn't matter how far away you go, as long as the thing going is no bigger than those two objects. So whatever your object you're using to measure the charge, that object, okay, I'll make it both colors just for clarity. That object, as long as it's the same size, you can sort of see that it'll always block the force from the red thing. None of the straight line force could possibly reach it, no matter how far away you put it, where obviously the black force can reach it. So the only force that's going to be relevant is the plus 3 charge, the minus 3 charge, and it's really just the point is how much does it get degraded by the fact that there's some tendency perhaps for the charge to migrate stronger to one side than the other side, just as a matter of the fact that it's going to be attracted, which is, there's going to be a low pressure and it's going to move towards the low pressure. Alright, so yeah, that might be enough for that segment of it. So I don't think it's an r cubed rule. It's somewhere in between, somewhere in here, but it's neither r squared nor r cubed. It's r 2.5 or whatever, some other r. Alright, so we'll do some more video in the moon part and try to keep this as concise as possible. So we'll play a little bit in here just so you get the idea that he does his math.
Get 1 minus d over 2r, with the square, of course. Now I single out the term 1 plus d over 2r to the power minus 2, and 1 minus d over 2r to the minus 2. And if you have a little bit of knowledge of algebra, you know that to a very high degree of accuracy, 1 plus x to the minus 2, if x is way, way smaller than 1, is 1 minus 2x.
So this is the part where it kind of illustrates that they make assumptions. So he's just assuming that it really doesn't matter. There's no idea of blocking anything. So he's basically just saying, what's the force on one, what's the force on the other, and I'll combine them as if one can't be blocking the other. So he's just saying they're this, essentially. You know, one's behind the other, but it's not being blocked by the other kind of thing. When there is a difference between this and this. And I don't think their math appreciates that difference or cares about that difference or pays any attention to that difference. So he's making an assumption here and just saying, well, we can just do the superposition argument and just add the forces. And you can't just do that, in my opinion. Play a little bit more of this for the people who care about math.
And 1 minus x to the power minus 2. If x is way smaller than 1, is 1 plus 2x. And I've done that here. So I'm going to replace now this term by an r squared outside, also here by an r squared outside, and the inside then becomes this. So you see here the net results. You see this r squared here, which I've taken out. And you see, as I promised, here you see 1 plus d over r minus 1 minus d over r. And the algebra of this is trivial. The plus 1 eats up the minus 1, and the plus d over r with minus d over r becomes 2d over r.
So again, he's just obeying a superposition, just doing the addition and subtraction, and coming up with an answer for as if there were just any distance, and it just doesn't matter whether they are in alignment or not. Alright, so let's get to the part where he equates this to the moon and gravity, which is kind of a leap.
But I wouldn't be surprised either if many of you sent me a solution that they believed that the electric field here is 4 times higher.
So he pointed to the wrong place. Well, it's 4 times higher than the one that's further away. So he's taken away the other image, so that's why he said it that way. And it's 8 times higher. And I would have guessed the 4, but my guess was based on superposition. I was already doing the superposition and saying if I take a point, whatever you want to call it, label it R. No, can't use that. C. No, can't use that. Come on, it's got to be one of the letters they haven't used for something, right? F. I take a little F and I put it somewhere forward, and I say I know what the charge is at that location. Well, from that location, then I can do the r squared rule and just say what would the charge at that location be at some other further down, and that would be the r squared rule. So that's how I was doing it. See, there's all kinds of different ways you can set up a mathematical equation, and depending on how you set it up, you do different kind of math, and that's the trick of some of this stuff.
Then at the location 2r, because they are so used to think that electric fields fall off as 1 over r squared. Yes, that's true for single charges, but not for electric dipoles.
But again, it's not really a dipole when you have positioned the dipoles in alignment. So that would be my argument. It lacks dipoleness then.
This phenomenon that the net force falls off as 1 over r cubed is well known also in astronomy, what we call tidal forces. Here we have the Earth.
So this is a little bit, yeah, we'll play all of this part just because it's, some of it can get a little bit sloppy. I mean, in terms of keeping things straight.
Mass m1, radius r1. And at a distance very far away, little r is the moon. Mass m.
Yeah, well, it's not that far away. I mean, it's far away, but it's really not that far. I mean, 250,000 miles is not that far.
And little r is way, way larger than r1.
So he said it the wrong way again. Little r is way, way smaller than r1. the moon's radius much smaller, not larger. Semantics, but you know.
Want to know how much larger? 60 times larger, roughly.
So the Earth is 60 times the diameter of the moon. Which isn't, you know, I almost thought the moon was a little smaller than that, but, you know, not bad.
The force at which the moon and the Earth attract each other is trivial.
So again, I would argue that even saying the force that they attract each other is incorrect in the sense that the Earth attracts the moon and the moon attracts the Earth, and they're two independent forces. They're, yes, happening at the same time, and they're being induced by each other, but they're not one. They're yin and yang. I mean, they have to take their turns as independent functions. It's not one cause. It's not one. They're both moving, even though we don't see the Earth move towards the moon. The center of the Earth's gravity, that is its mass, actually does move that way more than it moves in the opposite direction. So it does, in a sense, move towards the moon. It's just that because the moon rotates and the sun's rotating, I mean the Earth and the moon are rotating around the sun, that movement gets disguised. But it is wobbling in space because of the moon pull on the Earth.
1 and 2g divided by this r squared. However, this point of the Earth is closer to the moon than that point of the Earth.
Alright, so that's a simple argument, but I'll go to the illustrations just to be clear on what we're talking about. I might as well flip this over, I guess, and start all pretty and new. Alright, so we have Earth, and then we have Moon. And the idea is that the moon has an effect on the Earth in terms of its. You sort of have to think in a way. This is at least the way I think about it. Is that the stuff on the Earth, especially things like water, they're really orbiting the Earth, but they're not really stuck to the Earth. So in a sense, they're sort of orbiting it, and they have a centrifugal force because of the Earth's rotation. So as the Earth rotates, the stuff on the Earth, in some sense, has a little bit of pressure going out. All right, even though it has the gravity pressure pulling in, it has a little bit of pressure pulling out. All right, so I think that's something sort of important to understand. But let's continue with his description, and we'll go back to the drawing. So yeah, it's just a simple thing. Now we're just going to say, why are tides happening in a sense?
And so the pool here is somewhat larger than the pool there.
And the point would be is that still doesn't explain why the larger pole, you could see why that would see. You can't see it, but on his drawing he has a little bulge, okay? And he has it bulging on both sides. So you're saying, well, yeah, you can understand why this bulges, but why would the part on the other side bulge out if there's less pull? Doesn't mean any that wouldn't give it cause to bulge out. That would just give it cause not to push in. Because you're saying sort of it should be, yeah, I sort of have to go back to the drawing. Okay, it's not that big a deal. So the idea is you can sort of understand why this side would bulge out a little bit because there's the moon. But why would this side bulge out? Because you're sort of saying this pulling force is a force going in. It's pulling this surface in, and even if it's weaker than this force pulling the surface off, pulling this water off, even if it's weaker, it's an in force. It's not an out force. It shouldn't make the water go out here. It should make the water come in, and just come in less than maybe at some other location, but I just mean it's not in the same direction. So there's no reason to think it would make the Earth wider on both sides Okay, so that's what we're talking about, right? We're talking about something getting wider on both sides because something was here. You could understand why it would get wider this way. This doesn't really make any sense. Why would it go wider that way? It's still getting pulled this way. It's just getting pulled this way weaker than it gets pulled out. So this force is stronger, the pulling out force. And all you're really saying is this pulling in force is weaker than this pulling out force, but it's still a pulling in force, not a pulling out, pushing out force. So this explanation of unevenness doesn't really work in explaining why there's still a high tide over here. Okay, why is there a high tide on the opposite side of the moon? Right? The moon's here. Somehow I'm on the opposite side of the Earth and I have a high tide, when that should be a low tide if it's less pull, you would argue. And this is more pull, so it's the higher tide. Okay, so that's sort of where we are. And I need this, and then I hit that.
And that has the result that the Earth becomes slightly ovalated, like the green curve that I have here. And the difference between these two forces falls off as 1 over r cubed.
Okay, so the difference between these two forces, it just doesn't tell me anything. So, in a sense, I found that unhelpful as a statement. You really can't do anything with it. So the difference between these two forces, so the force here and the force here, this is an r cubed rule. Meaning somehow this force is 8 times less than this force if it was an equal distance. So you can't really use the 8 times thing, but this one's by the r cubed rule, so it falls off as you double the distance, it would be 8 times the degrade in the force. So I don't know how to exactly, I can't really use numbers unless there's a third distance to apply the numbers to. So, I don't have this distance is pretty small, whatever, 4,000 miles or whatever it is, 6,000, I can't remember the diameter of the Earth. So it's only a 1/5 of the distance from the moon to the Earth, but 1/5 is still some distance. It's not insubstantial. I mean, not 1/5, 1/20th. But he's saying there's an r cubed relationship somehow between this force and this force, where I think the more interesting subject would be, what's the force here? And what's the force here? But anyway, we'll get to that maybe. Maybe.
That same r cubed for exactly the same reasons that the electric field overlapping dipoles, as long as you stay on the same axis, also falls off as 1 over r cubed.
So he says the same reasons, and this is another point where I think, no, that's not going to be true. See, gravity is, it doesn't care, how much stuff you put in the way, right? Because gravity's all adding, because it's all one force. It's all the attraction thing happening. Now, attraction is really just the absence of pressure, which means, that it's getting pushed from the outside, things are getting pushed together. But I'm just saying, it's very additive. You can't block gravity. I can't put a bigger thing in the way of something. You say, oh, I can't see the thing behind it anymore. So the gravity adds up. These two masses add up as a new circle, essentially, and that's the gravity. So it stays r squared. He's talking about a specific thing from one side of one object to the other side of the object is r cubed. Again, I don't think it is, and this is one of those cases like with Huygens, right for the wrong reason. There's more of a difference. It's not the r squared rule when you're going through the Earth, and when the Earth is a spinning object. There's lots of reasons. But anyway, let's play some more of this. And yeah, we're okay because I'm not drawing. Okay.
So that is responsible for tides on Earth. And not only on Earth, but on all binary star systems, or all systems, stars and planets. There are tidal forces. And in our case, the moon's...
So again, the tidal forces really do depend on how liquid the surface of something is. So I don't even think you can really say it. You know, tidal forces. I'm not too sure there are such a thing when you don't have this idea of the surfaces not being rigidly connected.
Influence on us is larger than the influence of the sun on us, so that's why I've only taken the moon here.
Yeah, well, the sun's influence is so irrelevant. So when you think about the 10 meters per inch, I mean 10 meters per second speed that you're falling towards the earth, and you have to have the sun on the other side where you're falling, the amount of extra the sun adds. So you're going 10 meters per second, and the sun would add 0.004 meters per second. So it would add a tiny fraction to your speed. Or it would take away, if you're on the other side of the earth, from your speed, a tiny fraction. That's how weak the sun's gravity is at the location of the earth. It's just the earth is so big and it's moving such a great distance around the sun. It has so much time to move its path, to be deflected. It doesn't have to move more than that tiny fraction because it's in such a wide, long orbit.
So if you're here on Earth, it's high tide for you. Then since the Earth rotates, let's say in this direction, when you're here, it's low.
So now he's looking from the top of the Earth. All right. So that makes it a little more confusing because I was doing it the other way. But anyway, so he's looking down from the North Pole, let's say, and talking about as the Earth rotates. See, to me, that the Earth rotating doesn't mean much because the Moon is still in the same place. So he's got us rotating this way, which is the wrong way, I think. But anyway.
Tide for you. 12 hours after you were here, you have high tide again. And 12 hours later, you have high tide again.
So I would argue, all right, so I guess we can, I think that's all he really says, but we'll go back to it just in case, but I think that's all I think that's the end of his analysis, and I just think it's an underdeveloped analysis, because I think it's a lot more complicated than that. So I would argue that, yes, this doesn't bulge for no reason, okay? It bulges because of the centrifugal forces, and that's why the water tends at the equator tends to be thicker. Is because of that centrifugal force is allowing there to be a little bit more of a pull against gravity, and so there's a higher likelihood of thickness in the water there, you know, being pushed out. And the only thing that really is happening with tidal forces is the moon's gravity is stripping things from these angles. So what it's really doing is creating the low tides, in a sense, because it's pulling not only from the top down and the bottom up, it's pulling from the sides. Okay, so if from my model, you know, this is inside the Earth. You know, I'm looking at the Earth with the North Pole here and the South Pole here, kind of thing. It's being pulled from this whole side. You can just think of this whole side of the Earth as getting pulled, and this other side's getting pulled, and that's creating the low tides. So the low tides are essentially the thing being created, and when you create the low tide, you're obviously pulling water towards this higher tide area, but at the same time this water is already, it's centrifugally decided to stay where it is. I mean, it's already got some pressure saying go this way, and it's not as likely to be dragged along because it doesn't have to be. So the only water that gets pulled is this half, and this other half just kind of stays there, and a little bit of it gets thin here, and it just kind of, you know, but it doesn't really disturb this stuff that's already in motion, already has a velocity. So if you sort of think of this like if you just thought of about the water as an orbiting body, you know, something just going in an orbit, and then you had a moon here. Okay, so just imagine this thing has an orbit, even though there's nothing in the middle to keep it in orbit. You know, just pretend it has a velocity this way and it's accelerating inward constantly. Then you can sort of understand, I think, kind of, that the force you're really adding up is this inward force, you know, that's keeping this thing in its shape, and you're just recognizing that this is going to influence it as it goes around. It's going to pull on it this way against that motion. It's going to accelerate this motion, this is the motion it's going to have the least effect on, the one furthest away. So it's going to have the most effect on the motion on this side, and the effect is basically going to be pull stuff so it doesn't stay here very long, and it doesn't get here easy. So you're pulling off these sides, and that's really what's making the water have to go or stay here and here. Is there's less pressure pulling this water in, and so it stays this way. So it's like its natural state. It's not like a high tide, it's just a not affected tide. This is the true high tide, and these are the low tides that are causing the whole problem. That kind of thing. So I think it's something like that. So it's a bit more complicated than just the distance from the moon. And it just can't be just it's gravity. You can't compare it to charge, because gravity is additive. You can't block gravity. If I put another pen moves behind this pen, I double this gravity. I make this gravity much stronger. Or if I move a charge behind another charge, I make this charge disappear. I think that's a truth. And you know, I just don't think there's any experimental evidence that's been done to verify that their assumptions of their mathematics are actually correct. I mean, this is an experiment that probably can be done. You can take two charged metal spheres, maybe, opposite charges at a sufficient distance away from each other not to affect each other too much, and then maybe use a test charge to see if you can, you know, a test charge smaller than the two main charges, and see if you can detect this charge through the other negative charge from here.
Very roughly, you have high tide every 12 hours, low tide every 12 hours. Since the Earth is also moving relative to the moon is around the Earth, it's not exactly 12 hours, but that's irrelevant right now. The basic idea is clear here, that since the Earth rotates, if we assume that the moon is not moving, then between here and here will be 6 hours, between here and there 12 hours, between here and there again you are low tide 6 hours, and between here and here another 6 hours.
So again, but it does matter whether the water, so by rotation, is moving away from the moon or whether it's moving towards the moon. These are all things that I think have to be considered. Yes.
I would recommend that you use Google and look up tidal forces and see actual simulations.
Again, yes, simulations based on their mathematical model. So again, not simulations based on measured facts or anything like that. You know, some sort of real experiment.
Which is very nice, whereby you see objects rotating under influence of an object very far away. So you see the oblateness, and then you will see if the object rotates, that the oblateness, of course, stays in the same direction. It's very interesting. So look up tidal forces.
So again, I don't think these two subjects can be blended together, and I don't think either one is, strictly speaking, mathematically accurate to say it's an r cubed rule. I think the rule is that there's a lot of things changing those two tides, and just as in the charge circumstance, and the effect is something in between the two.
And by all means, look up electric dipole fields. Keep in mind that if you were to look at this point or at this point, that the E field does not fall off as 1 over r cubed. It is only very accurately 1 over r cubed as long as you stay on the line that connects the two.
And that's only true if you assume the plus charges move right through the negative charged object, as if charges are gravity, and they're not. They're a form of gravity, don't get me wrong, but they won't do what magnetic dipoles and charge dipoles and synthetic dipoles are not the same as gravity, which doesn't have any polarization.
All right.
Where polarization is moot because it's randomized, so it doesn't have any, none of it's segregated, so therefore it can't magnify effects.
Today is October 12th.
Okay, so that's it. Yeah, so that's enough of a video. I won't drag it out. Yeah, I didn't put him back on, sorry. Left the drawing. See, I forget things. I overlook. Error. A little bit. Okay, so I made a little error. Alright, well, anyway, so till the next time, and such.